In this tutorial, I will show you how we can design slab in SAFE 2020. Before going to SAFE, we have to take decision about the thickness of slab. Here you can see, as per ACI code or BNBC 2020, minimum thickness for one-way slab should be L by 20 for simply supported, L by 24 for one end continuous, L by 28 for both end continuous, and L by 10 for cantilever slab. This expression is applicable for normal weight concrete and Fy equals 60,000 psi. For Fy other than 60,000 psi, the above expressions shall be multiplied by 0.4 plus Fy divided by 1 lakh. Now for a two-way slab, minimum thickness should be perimeter divided by 180. Here we will use these equations just for initial design check. If we get higher deflection than the limit of our code, in that case we will increase the thickness, otherwise these will remain same. Let me explain more clearly. For this span, which is 16 feet divided by 22 feet, required thickness will be 16 multiplied by 2 plus 22 multiplied by 2 divided by 180. That means 0.42 feet. Now multiply this one with 12. We are getting 5.06 inch. But in this tutorial, we are interested to use 500 W steel. That means 72.5 gauge steel. As a result, we have to multiply this value with 0.4 plus Fy divided by 1 lakh. Let's calculate 0.4 plus Fy, that is 72,500 divided by 1 lakh. We are getting 1.125. Now multiply this one with 5.06. We are getting 5.69 inch slab thickness for this span. This is the highest two-way span. Now calculate a similar thing for this one-way span, which is 10 feet and one end continuous. Actually two end continuous here, this one, and okay, actually this is one end continuous here. This direction is one way, so this is one end continuous. So the equation will be L by 24. So 10 divided by 24, we are getting 0.416 feet. Multiply this one with 12, we are getting 5 inch. Now multiply this one with 1.125 as we did earlier. So we are getting 5.625 inch for this one-way span. Basically for these two one-way span. Here these and this span, these two span is one way, other spans are two way. Now for initial design check, we are using slab thickness as 5.5 inch. Then we will check its deflection. If we get calculated deflection higher than the limit of our code, in that case we will increase the thickness, otherwise it will remain same. So now we can go to SAFE, go to File, New Model, use Built-in Settings, ACI 31814, click on OK. Custom grid spacing, edit grid data, display grid data as spacing. In X direction we have A to D grid, and in Y direction we have 1 to 4 grid. For X direction, grid spacings are 14 feet, 16 feet, 10 feet. So 14 feet, 16 feet, 10 feet. For Y direction, dimensions are 22 feet, 14 feet and 22 feet. 22 feet, 14 feet and 22 feet. Click on OK. Now go to story dimensions. Here name of a story below, that means base. Here we will use 10 feet. Name of a story above, that is story 2. Here we don't need any story above, so we will use 0 here. Model datum, that means story 1. That means story 1 to story height below, the distance will be, or the height will be 10 feet. Okay, that means we are considering a single story of 10 feet height. Click on OK. Here you can add another window to see the 3D view of this model. Now we can save this one. Go to define material properties, add new material. Concrete 3000 psi. Click on OK. Name it concrete 3000. Here design property data 3000 psi. Here we are designing this slab for stone chips, so modulus of elasticity will remain same. Click on OK. Add new material, rebar. At first select grade 75. Click on OK. Rebar 72.5. Now go to design property data. Here we will use 72,500 for minimum yield strength, 96,400 for maximum tensile strength, 79,750 for expected yield strength, and 1,06,000 for expected tensile strength. 72,500, 96,400, 79,750, then 1,06,000. Okay. Click on OK. Click on OK. Now we have to define section properties. So go to define section property, delete multiple properties, select them all and delete. Now select all except one, then delete. Click on OK. Add new property, select rectangular section. At first we will define column, that is C 12 by 30. From CAD you can check its dimension, 12 by 30 inch each column. Okay. From material we will select concrete 3000 psi. Width will be 12 inch and depth will be 30 inch. Go to property modifiers. Here for moment of inertia about 3 axis we are using 0.7. For 2 axis also we are using 0.7. Click on OK. Click on OK. Now define beam, add new property, rectangular section, B 12 by 24, material concrete 3000 psi, width 12 inch, depth 30 inch, depth will be 24 inch. Property modifiers. Actually here we are not designing column or not designing any beam, but when we design beam in ETABS, sometimes we have to use torsional constant as 0.001 or 0.01, which generates some additional moment in slab. To calculate or to reduce that moment, here we can use moment of inertia about 2 axis as 0.35 for beam and also 0.35 for 3 axis. That means for 2 and 3 axis we are using 0.35, which will generate or design some additional extra top or negative reinforcement in our slab. If we use 1 here, we will get more economical design. But if you design beam but using torsional constant 0.001 or 0.01, in that case you can follow this procedure. Click on OK. Section type, here we will select beam section, then go to design property data. Here we will select rebar 72.5. Sorry, we named this one 725, this will be 72.5. Okay, click on OK. Click on OK. Define material properties, modify. This is not very mandatory. 72.5. Okay. Now we will define slab section. Go to define section property, slab section, add new property, slab 5.5, slab material concrete 3000, modeling type will be shell thin. Here already you know the difference between shell thin and shell thick. Here we will not consider slab as membrane. Okay, we will use shell thin or shell thick. Here in our case this will be shell thin. Now go to property data, thickness we are using 5.5 inch. Now click on OK. Click on OK. Now we can start modeling of our structure. So go to quick draw column. From here select property below C12 by 30, property above C12 by 30. But we need to change its orientation. So we will use angle degree 90 and click here. You can model them all at a time. Now we will model here beam. From here we will let me check one thing. This height will be 120 because here we are considering 10 feet height. Okay, so go back. Here we are using property below 12 by 30. Here there is no property above. Okay, that's fine. Now angle degree 90. Here we will use 120 inch. That means height below is 10 feet. Now you can model them all at a time. Now we will model beam 12 by 24. Now we can model slab. So go to quick draw floor. From here select property slab 5.5 inch. Just model them. Now we have to assign dead load, not dead load, wall load, partition wall load, floor finish, live load, etc. So go to define load pattern. At first we will define here wall load, type will be super dead, add new load, partition wall load, floor finish, live is already present here, so we don't need to define live load again. Click on OK. Now select all beams, select object type, beams, select close. Here we will assign wall load. So go at first change the unit, go to assign frame load distributed, wall load. Here we are using 6 kilonewton per meter. Already you know all the calculations because you must know clearly about ETABS. So just as like ETABS, here we are using 6 kilonewton per meter wall load, or you can use 7 or 8, etc. Whatever you get as per your calculation. Click on apply. Click on show on deformed shape. Now we will assign partition wall load. Here we are not modeling any null line. Here we will select all the slab and we will assign partition wall load as 2.5 kilonewton per meter square. So select all the slab, then go to assign, go to shell load, go to uniform, then go to partition wall load 2.5 kilonewton per meter square. Okay, you can assign partition wall load as per your calculation, or you can also model null line here. Okay, apply. Now we will assign floor finish, that is 1.20 or 25 psf. Apply. Then we will again apply live load here, that is 2 kilonewton per meter square. So we have completed assigning all the loads. If we select this one and right click of mouse, we can see here we have assigned floor finish, live and partition wall load. For all the beam we have used loads 6 kilonewton per meter. Now go to define, then go to mass source, then go to modify / mass source. Here we will use specified load patterns: dead load 1, wall load 1, partition wall load 1, floor finish 1, then live load. Here we are using 0.25 as all the values are less than 3 kilonewton per meter square. Okay, click on OK, click on OK. Now select this whole structure and assign mesh here. Go to assign shell, floor auto mesh, auto rectangular mesh. Here we are using 300 mm. Apply. Okay. Till now whatever we have done, we have completed modeling, then we have applied all the load, we have defined load pattern, defined mass source. Here we don't need to assign diaphragm. We can select this one. Here I am not getting any option for diaphragm, that means this is not necessary here. Then we have completed meshing. Now we have to define load combination. So go to define, go to load combinations, add default design combo, concrete slab / beam design, convert to user editable. Okay, here this is this load combination is for scale factor 1.4. This load combination is for 1.2 dead load and 1.6 live load. Here we will define another load combination, which is a service load combination. Dead, wall load, partition wall load, floor finish and live load. Okay, this is the service load combination. Click on OK, and this will be our desired load combinations for the final design of the slab UDCON S2. Okay, now what we can do, we can go for run analysis. Okay, here in SAFE we need to define design strips also. So go to draw, go to design strip. Here I am using design strip as at first change the unit. .25 into 22, that means 5.5 feet will be enough for us. 5.5 feet or 6 feet, that means 72 inch we can consider for left, right, end left and end right. Okay, we are using 6 feet design strip for both left and right, start and end. Now go to this grid. Why I am not getting this option? Okay, go back, draw design strip. Here we are considering 72-inch design strip. At first we are taking column strips. Okay, now we will take some middle strip. But we can't snap mid zone here, so go to draw, snap option. From here select this one, click on apply. Okay, now okay, similarly we will go for design strip B. At first we will go for column strip. Similarly we will define middle strip. Here you can increase the size of your strip as per your requirement. Here I am just using L by 4. You can also use L by 3, which will be more better. Okay, that means here I have divided this span by 4, right? You can divide this one by 3. In that case we could take design strip or of 7.3 feet. Not a big deal. Now we will go for analysis. Before that we can check model, similar like ETABS. No warning. Now go for run analysis and design. Okay, here safe showing us the displacement value. Okay, here this is okay. Here we are getting this displacement value in mm. We are getting 2.97, but this is not for our desired load combination. We will go to display, show deformed shape. From here we will select combo, then we will select service, click on apply. Here we are getting only 7.9 mm displacement, which is the maximum one. We can also check for UDCON S2. This is coming around 11 mm or 10 mm. Now what is the limit from our code? Here I am showing you BNBC 2020. Our slab is supporting its partition walls. Okay, so we are considering here roof or floor construction supporting or attached to non-structural elements not likely to be damaged by large deflection. In that case our limit will be L by 240. Okay, now for the two-way slab, which was 16 feet by 22 feet, that means we can go with 16 feet, right? That means 16 feet multiplied by 300, we are taking this to mm. Then we will divide this value by 240. Okay, divided by 240. Here our limit is 20 mm for this two-way slab, and we are getting only 10 to 11 mm. Now check for this 10 feet span. We are getting 10 multiplied by 300 divided by 240. Our limit is 12.5 inch, and we are getting calculated deflection 10 mm. Actually, if we consider this one for service condition, in that case we are getting only 7.9 mm. That means our slab thickness is okay for this design. Okay. Now we will go for reinforcement design of slab. At first, change the unit to US default, then go to display, show slab design. From here, select impose minimum reinforcing. At first, we will design layer A and we will design top layer rebar for layer A. So uncheck bottom rebar, click on apply. Here you can see the moments acting at the support. Then from here, select plan view. Go to uniform reinforcing, typical uniform reinforcing. From here, I am selecting number 3 bar. At first, I will try with 10-inch spacing. You can see that for some locations, 10-inch spacing top rebar is not sufficient. So we will go for 8-inch spacing. Still, this is not sufficient for some locations, but for all other locations, this 8-inch top rebar spacing of 10 mm dia rebar is sufficient. When you will design practically, you can go for span wise. Suppose for these spans or for these sides, you can go for 8-inch center to center distance of top rebars. But for these panels or for these two zone, for these two outside zone, you have to reduce the spacing. So let's go for 6-inch spacing. This is still not sufficient. Go for 5-inch spacing. This is sufficient for throughout the slab or for whole slab actually. So we have taken decision about top rebar. There is two different thing. One is top layer rebar, other is extra top bar. When I will show you the detailing, then it will be more clear to you. Now go for bottom rebar for layer A. Here you can see, select none, then click on apply. Here you can see the positive moments acting. Then here from here you can see the 3D view also. Fine. Then go to the plan view again, typical reinforcing. From here select number 3 bar, go for 10-inch spacing, click on apply. You can see that this 10-inch spacing is sufficient. Now we will go for detailing. At first you have to understand that you have designed layer A. That means reinforcement will be placed perpendicular to the layer A, right? So go to AutoCAD. At first we are designing these reinforcements. So from here copy this one, CO. Here I will select 10 mm phi rebar at the rate of 5-inch center to center, alternate crank. If you design like this way, what will be the situation? 5-inch center to center alternate crank. That means at support zone, the distance between the two bottom bar will be 10 inch and the distance between two top bar or two crank bar will be also 10-inch center to center, because this crank bar and this bottom bar will be placed alternately. If you have minimum idea about reinforcement binding of slab, you can understand this more easily. Okay, so here I am selecting 5-inch center to center. As the result, spacing between top and bottom rebar will be 5 inch, but spacing between two top bar or between two crank bar will be 10 inch, and also spacing between two bottom bar will be 10 inch at support zone. But for the mid zone, this spacing will be 5 inch because this crank bar will be bended down at mid zone, right? So if we suppose here we are interested to provide 6 inch center to center, we can't do so because as a result what will happen at mid zone, this is fine because we need a spacing of 10 inch bottom bar at mid. But what will happen at support? Here the spacing between two bottom bar, here the spacing between two bottom bar will be 12 inch, but our requirement is 10 inch. As a result, we can't select 6 inch or 5.5 inch. We have to select or we have to provide 5 inch center to center alternate crank bar. Now go for the design of top rebar. Here we have already placed crank bar as top bar at the support zone. Now we have to take decision about the extra top bar. From safe you can see that required distance of top rivets at support zone is 5 inches. So if we place or if we provide 5 inches center to center alternate crank bar, in that case the spacing between two crank bar will be 10 inches, which is not satisfying our design requirement. As a result, we have to provide a extra top between two crank bar at each position. Suppose, let me explain you more clearly. Suppose this is a crank bar, this is a crank bar, this is the crank bar. Here O enter 10, spacing between two crank bar will be at 10 inches as we said earlier. CO enter. Suppose this is the plan view, right? But we need top bars at 5 inch spacing near the support zone. Okay, so what we have to do, we will provide a 10 mm bar as extra top up to the length of L by 3 or L by 4 at all support zone. So what will happen as a result, suppose this is the extra top rebar. So what will happen, the spacing between the top layer or top rivets will be 5 inch center to center, which is same to our design requirement. Okay, now we will go for layer B. At first we will design top rebar for layer B. From here select none, then click on okay, we don't need here, select this window, then click on apply again, then go for typical uniform reinforcing. For top rebar, here at first I am selecting 10 inch center to center, not sufficient. Then go for 8 inch center to center, not sufficient. Note that for some panel this is sufficient. For these panels you can go for 8 inch center to center spacing, no issue. But for this zone you can't go with 8 inch center to center spacing of top rebar. So we can go for 6 inch center to center. Still this is not sufficient. So we will go for 5 inch center to center, but still this is not sufficient for some zones only. So we can try with 4.5, apply. Now this is fine. Okay, so for top rebar at layer B, we have to provide 4 inch center to center spacing of reinforcement. Now go for bottom rebar. From here select none, go for apply, then typical reinforcing. Go with at first try with 12 inch spacing. This is not sufficient. Go for 10 inch, not sufficient. Go for 6 inch. This is sufficient. We can try with higher values, suppose 7 inch. Okay, this is fine. Also for 8 inch maybe not sufficient, so we can go for 7 inch, right? But what will be the final detailing? What will be the final detailing? Here we can go for similarly 5 inch center to center alternate crank, or we can go for 6 inch center to center alternate crank, or okay, no, sorry, here we can't go for 6 or 7. Basically here bottom reinforcement requirement at support zone is 7, right? So we have to go for 3.5 inch center to center spacing. We have to go for 3.5 inch center to center spacing of the bottom bar. As a result, if we go for 3.5 inch center to center spacing, what will happen? If we go for 3.5 inch center to center spacing, here, suppose here I am writing 3.5 inch center to center spacing, 3.5 inch center to center spacing. As a result, what will happen? At support zone, the distance between two bottom bar will be 7 inch, okay, which is sufficient as per our design requirement. Fine. And the spacing between two top bar and between two bottom bar will be 7 inch also, but our requirement is 4.5 inch for top rivers. As a result, what we will have to do, we have to assign a extra top between two crank bar. So what will happen? Suppose this is a crank bar. This is a crank bar. Here spacing is 7 inch at support zone. I have already explained. Okay. Now, as per design requirement is 4.5, which is not sufficient. So we have to provide a top rebar. Suppose here we will provide a top, actually not top rebar, here this is called as known as extra top rebar. Okay, so this is the color. As a result, what will be the situation? The spacing will be around 4 inch, not actually 4, this will be 3.5. okay, this will be 3.5. Here this is spacing is 7 inch. So if we take a if we provide a extra top at mid between two crank bar, in that case the spacing will be 3.5 inch center to center between the top rivers at support zone, which is sufficient for our design. That's all for today. See you in the next tutorial. Thank you.